Hey guys, welcome to day one of the virtual notes. Remember, these are designed to help you, and ideally we'll have more time in class to reinforce the concepts we learned. So, go along with your guided notes as I'm going through them. And at the end, you should have them all filled out. If they're not, if you have anything blank, you're more than welcome to rewind, rewatch the video. But please don't forget there are some things you may have to fill in with the book. Also, as we go along, if you have questions, make sure you record them down at the bottom of that Gas Laws Guided Notes page that you're filling in. These questions will be a great way to start off class tomorrow, and that way we can really get going on a good start. So, clearly you're the smartest kids in the world, and I bet you can guess we're talking about gas laws. So before we talk about the laws today, quick review on what you already know. You know that gases have no fixed shape or volume. In other words, whatever container we put them in, they will take that shape, they will take the volume of that container. But there is a relationship between pressure, volume, and temperature. This is going to be the guiding premises behind today's notes. We're going to be able to eventually do some calculations and be able to explain 3 laws that will help talk about this. Here are our 3 laws: Boyle's law, Charles's law, and Gay-Lussac's law. Each one of these will have one condition that's remaining the same, while the other 2 variables will change. Here's the equation that will guide our entire day. We have P1 V1 over T1 equals P2 V2 over T2. Now, P stands for pressure, V for volume, and T for temperature. The way this is set up, we're going to give you an initial temperature, pressure, or volume, which will go under the P1 V1 T1 side, and then we'll give you a final pressure, temperature, or volume, and that'll go in the P2 V2 side. And then you'll solve for the variable that we did not give you. Keep in mind, one of them will always be held constant, so you'll only have one variable to solve for. Remember, if I'm moving too fast today, guys, you can and pick right back up where you left off. So, let's move on. If you're not ready, pause it and record whatever you need. The units for this equation. You should remember back from when we talked about scientific method and SI units that the unit for temperature, although we like to use Celsius and Fahrenheit, the technical SI unit would be kelvins. So in any problem we give you, we're not going to give you temperature in degrees Celsius or degrees Fahrenheit. It'll be in degrees Kelvin. So pressure is in atmosphere, and I know you've probably never heard that, but we'll talk about tomorrow where that came from. And then volume is the easy one, the one you already know. The unit for volume is liters. We're going to fly through this. These are kind of the things we're going to talk about tomorrow with a barometer, atmospheric pressure. Talk a little bit about what is standard pressure, all the units involved. But we're going to dive right into the first law, and that is Boyle's law. Remember, P1 V1 over T1 equals P2 V2 over T2. That's the equation you're going to use, but we're going to simplify it slightly. In Boyle's law, we will always keep temperature constant. In other words, during the initial conditions here, in the beginning of the equation, they are going to be different, or excuse me, the temperature will be the same in the final part of the equation, or the second part. So we can say, if temperature remains constant, the volume and pressure vary inversely. So here, over here in these boxes, we can fill these in quite simply. So inversely means opposite. That says simply if pressure, let's say, decreases, then our volume is going to increase. Or vice versa. We could say if pressure increased, then volume would decrease. Either way, they need to be the opposite of one another. And that's what Boyle's law says. That if we keep temperature constant, that pressure and volume will vary inversely. Notice in our equation down here, if we really want to do some kind of solving, that's a terrible circle. Absolutely ridiculous. I'm going to blame that one on the smart board. That P1 V1 equals P2 V2, and you'll notice in Boyle's law we didn't include temperature in the equation because we kept it constant. Boyle's law has a couple real-world applications. We're going to have an awesome marshmallow demo for you tomorrow. But you think about when you're in an airplane and all of a sudden your ears begin to pop. This has to do with Boyle's law. The fact that temperature is the same in the airplane for the most part, but as you go along, we have less atmospheric pressure out there, and all of a sudden you feel that popping because gas isn't escaping like it should be. We'll talk about a syringe tomorrow when taking blood. We definitely have Boyle's Law explanation there. Deep sea divers, we'll talk about what the bends are. So let's talk about Charles's Law now, guys. Remember, once again, if you have questions, please write them down at the bottom of the paper. And if I'm moving too fast, pause it. That's what the pause button is for. Charles's Law now, look at it. P1 V1 T1 equals P2 V2 over T2. Same thing, but now we're not keeping now we're not keeping temperature constant. Pressure stays the same. And this is kind of the key thing between these laws, is that we'll change what is remaining constant. And Charles's Law says if pressure remains constant, then volume and temperature are going to be inversely related. Once again, in other words, if temperature, let's say, increases this time, then volume is going to decrease. It's that easy. Once again, you can look down here at the formal equation for Charles's Law and notice that what did we leave out? Pressure. And we left out pressure because pressure was constant. We didn't care about it. Now, I know that equation kind of looks like a mess, so I'll rewrite it right here. V1 over T1 equals V2 over T2. Super simple, guys. We leave out pressure because it remained the same. Much like Boyle's Law had some real-world concepts or applications, so does Charles's Law. We can take a look at a few at those. Talk about your car tires deflating for those lucky few that can actually drive without mommy and daddy legally. Your car tires deflate on a very cold morning. They'll deflate because all of a sudden the air molecules within that tire are no longer moving as rapidly and they're not taking up nearly the amount of space. You can think of it as them kind of grouping together. We could say the exact opposite on a hot summer day, that our air tires would look more full than they would on the colder day because all of a sudden our air molecules have more energy, they're moving around a lot faster, they're taking up more space. The same goes for a basketball or a hot air balloon. Hot air balloon floats because when we heat that air up, it expands and all of a sudden our balloon begins to inflate. If we wanted it to go down, we do the exact opposite. We stop heating up the air. Imagine that concept, huh? We'll talk about a lot of these tomorrow, and we're going to do a really cool balloon demo for you on this one. Moving on, guys, to Gay-Lussac's Law, a crowd pleaser, the favorite of them all. And this one, we keep volume constant. And temperature and pressure don't vary inversely this time. They are directly related. In other words, if pressure increases, so will temperature. This is extremely important that you recognize that this one is a direct relationship and not an inverse relationship. If you look at the top again here, guys, you'll see that we're dealing with the same basic equation again. P1 V1 over T1 equals P2 V2 over T2. But when we use it for Gay-Lussac's Law, once again, if volume is remaining constant, we leave it out of the equation, and the main equation we want to use now is P1 over T1 equals P2 over T2. Remembering that we always leave out what we're keeping constant. And I'm going to tell you a way to remember that here in just a little bit. Ways to remember Gay-Lussac's real-world examples. Think about a cannonball, kind of the ignition there. That's what's going to propel that cannonball through the air. We're going to do a really cool egg demo with you tomorrow that's really going to help explain this law. But most importantly, you're going to have to work through problems. Just like any word problem we give you, we want you to kind of go about it the same way. So the first thing you do is figure out which law you're dealing with. In other words, look at what is staying constant. Write out your variables in your formula. Insert your known values into the formula. Solve for the variable, and please, 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 we see this so much, don't forget the units, because if you don't include the units or the units are wrong, guys, your answer is wrong. We hate to do that to you, but we have to. Now, there is a way you can remember these things, and here's how you're going to remember it. Big tigers can play golf violently. I know it sounds ridiculous, But this saying is going to help you guys remember what stays constant with each law. So, if we look at big tigers, we're going to think B and big for boils and T for temperature. In other words, Boyle's law, temperature remains constant. We look at can play, C for Charles's, and P for pressure. And then, of course, golf violently, Gay-Lussac's, and volume is a constant now. So, we'll talk about the popsicle stick when we get into class. Don't worry about that one down at the bottom. But right now, you need to remember, big tigers can play golf violently. B for boils, T for temp, C for Charles, P for pressure, G for Gay-Lussac, and V for volume. If you can remember those, you have a really big leg up for tomorrow's lecture. That's all I have for you guys. So if you don't have everything filled in on your guided notes, which I'm looking at right here, and I think I pretty much covered it all, remember you can maybe do some internet research. Oh gosh, don't worry about that. That would take forever, wouldn't it? Or go look through your book, guys. It's all there, I promise you. And tomorrow when we come into class, we're going to talk about some real-world examples, do some demos, and then we're going to practice actually working these formulas out on your own. Alright, have a good one. See you tomorrow, guys.